Today we're working with infinity categories, and so we need some definitions, and so infinity category. Okay. So infinity categories are an extension of ordinary categories that makes it easy to work with homology. So it's a kind of a formalism to fuse homology into category theory in a way that is very flexible, that you can easily transport structures along along quasi-isomorphic complexes and so on and so on. So what we fix is, well, we fix an algebraically closed field, algebraically closed field, and well, we want to use like C, but often because there are a lot of signs around, we often sometimes use one in characteristic 2, then we don't have to bother about the signs. So C or 1 with characteristic 2. And then we fix a group, for the grading, and so this G, so we can either work with Z or Z2, so we get Z-graded complexes or just Z2-graded complexes. And again, depending on the situation, we will move between the two. Okay, good. Okay, so let's see. So definition, an A-infinity category consists of, I'll call my A-infinity category curly C. So what are the ingredients? A collection of objects, can be a set or a class, collection of objects of C. And then, so for each pair x, y in of C, we have G-graded, so where G is our grading group, K vector space C x, y. Okay, so that's the home space between x and y, but it's Z-graded, so G-graded, so we have homes of different degrees. Okay, and then we have products, and these products mu k, they go, so we first we go from an object x0 to an object x1, then from x1 to x2, and so all the way to xk minus 1 to xk, and we land in C. We go from x0 to xk. So there are k spaces here, so it's a k area product, so this is k multilinear. and of degree 2 minus k, okay, where, well, you interpret 2 in RG as, well, you can interpret here as 2 and here as 0, of course. Good. And this degree 2 minus k, well, there's also there's also a different interpretation to view this as a product of degree 1 from the shifted versions, and then here it's degree 1. So you can either interpret this product just between the home spaces itself or between the shifted home spaces. And if you do it with the home spaces itself, it will have degree 2 minus k, so it will depend on our k. But if you do it with the shifted versions, it will always have degree 1. Okay. And then there are relations between the products. Relations. And this means, well, if I have some objects, some morphisms, A0, well, maybe A1, and then A2, and so on, until A something, then we can use one product, some mu k, and use a product like this. So we first take a product, a k product from something over here. So this goes from, let's say, to I plus 1, and then to a I plus k. And then we take another product where we fill in everything and combine it, okay, then we have eventually combined everything to one morphism, and we sum over this, we get 0. So you sum over all possible k plus L being, so if these are like n entries, then we have that, so we have, here there are k, and then, so this is k plus Sn minus 1, correct? So it's actually just means all the possible ways to combine this set of n elements with two products, and then there's a sign. Okay, and the sign, it's it's as follows. So you think of moving this one from behind to the correct position, so it has to jump over all these. It has to jump over all these a's until you get to the ai plus 1. So for each of all these things that you jump over, you add 1 minus degree. Oh, yeah, I'm going to do it in white. Okay. 1 minus the degree of a1, and then plus 1 minus, sorry, well, no, I meant the degree of a1 minus 1, sorry. It doesn't matter, of course, but let's, ai minus 1. So this is my dagger. Okay, and so this is, yeah, so this is one sign convention, but, well, there are different sign conventions around depending on which, where it's being used. So this is a sign convention that's usually used in symplectic geometry. So in the book of Paul Seidel on Fukaya categories, they use this, but in books on representation theory, often they use a different sign convention. But the idea is actually, well, the sign convention comes from something, well, the sign convention how should you interpret this? Well, actually, so there's a level on which there are no signs. So you can actually write this instead of using the elements in a tensorial way. So it's something like, this is actually mu L applied to a number of times the identity tensor some power, and then tensor mu k, tensor the identity to some power. In this case, it's I, and here let's say there's j. Okay. So basically, as a tensor product without signs, this is 0, and then there's a rule to interpret the signs. And that's a Koszul rule. And that says, well, if you have something like this, then and you want to apply this one to that one and that one to that one, then you should add a sign, the degree of f times the degree of y. So you jump f over y, and then it's f of x tensor g of y. Okay, and so this gives you, if you move everything from the right, you get this, and the fact that there's -1 here comes from the yellow ones there. Okay, because you interpret this as products between the shifted versions, and you move everything from the left. But of course, for the same reason, you could also have moved everything from the right, and then you get a different sign convention. So the signs are really a pain in the ass. So that's the downside of this explicit formula of A1 category, formalism of A1 categories. Okay, good. So, yes?
Just for the relation there, are we summing it over all, for fixed k, we're summing all possible types of...
Yeah, we're summing over all possible k and l, and all possible locations also. So you sum also over this I here. So it's all possible ways of smashing it together.
But for a fixed k, we're summing all of those, and then for each k, we have a relation as well?
No, for each n you have a relation. So there's a relation Rn, which is a relation on n entries, and that's what you get. And the relation for all n is this is important, k plus l is n minus 1 to get things right, and then there's the other index to see where you start. Okay. So let's, well, maybe it's good to look at these relations. So you have R1, what does it say? Well, in that case, there's only one way to compose. There's mu1 and mu1. So we have mu1, and we put it on A. So actually this gives you mu1 squared is 0. Okay. So for all objects, mu1 of mu1 is of A is 0, and mu2 R2 then actually becomes something like well, so we have A and B, and what can we do? Well, we can first do a mu1 here, and then mu2 it with B, or you can do AB, you do mu1 here, and then you do mu2, and then you have, of course, you can first do mu2, and then you can do mu1. And the sum with the appropriate signs is 0, but if you look at it, so this is a two-ary product, and this is like a differential, and so you see this looks like the Leibniz rule. So this is a graded Leibniz rule. Leibniz rule. And then let's do R3.
Sorry, could you repeat the sign again?
Can I, whether I want, you want me to do the signs?
Oh, no.
No, I don't want to do the signs, okay? There's a limit to the explicitness that I want to go. Okay, and so now the third one. So first I'm not going to write the mu's, so what you can do is you do this. You can also do this. Then there's some junk, including, well, so you can kind of do, well, you do mu1 of A, and then B, C, and then you do a mu3 here, and then there's also a mu3 like this, and you do mu1. So this is some junk, including with, or let's say containing mu3. Okay. So the idea is that if there's no mu3, or if the mu1 is 0, then actually this just gives you the associativity. So this is associativity plus junk. Okay, and so this means that actually we've already seen some examples. So what happens? So an A infinity algebra, A infinity category with only mu2 and Cxy concentrated in degree 0 is an ordinary category. Okay, and an A infinity category with only mu1 and mu2 is a DG category. Okay, so because you see then these three R's are the only one that matter, and they result into the ordinary stuff. But there's one caveat. So again, because of the signs, you have to say, well, d of A is -1 to the degree of A, mu1 of A, and A times B is -1 to the degree of B, mu2 A comma B. So this is to make it work. So in this particular sign convention, in other sign conventions you have to make other things. But the idea is we already know some A infinity categories, which are DG categories and mu2 and ordinary categories. And the thing is that these A infinity categories, they are really useful because you can kind of shift between DG categories or things which have, for instance, only a few products, mu1 and mu2, to include more products, but then you can go to maybe include, well, more, make your spaces bigger, and you make your products smaller, or make your spaces smaller and products big. So there's kind of a slide. So there's a slide. So the idea is, let me maybe make it clear. So we've seen you've always have mu2, again mu1, which squares to 0. This means that it's always a complex. The home spaces are always complexes, so it makes sense to work with homology. Now, if you work with homology in ordinary DG categories, then you know if you take homology and you forget about extra structure, then you lost a lot. And this A infinity business is to keep the structure when going to homology. Okay, so on the one hand, you have like DG algebras, which are big, because we didn't go to homology, but few products. And on the other side, you have what they call minimal models, where you have small, so these are big home spaces, and not very few products. These are small home spaces because we go to homology. And we have, well, a lot of products, a lot of higher products. And I'm going to make. And so this thing makes it, this setup makes it easy to slide from one direction to the other and back. And so for each infinity algebra here, somewhere in the middle, you can find a DG algebra that's quasi-equivalent to it, but you can also find a minimal model that's quasi-equivalent. And the choice you want to make depends on what you want to do. The idea is you want to sweep the junk under the rug, and so if you so here you swipe it under the rug of the big home spaces, and here you swipe it under the products. Okay, but you can move the junk around to where it doesn't bother you. That's kind of the good. So to go a bit more into detail, so the idea is that, so there's also a notion of an A infinity functors. And so what does it do? Well, it's also an extension of a functor. So we have an F0, which goes from, so F goes from some category A to some category B. And so F0 will go from the objects to the objects in B. And then F1 will go from, well, let's say from A x comma y to B f of x comma, well, f0 of x comma f0 of y. Okay, so this is an ordinary functor, and again you have fk's, which then go from, well, again so we start from an x0, x1, Then we go x1, x2, and so on until xk minus 1, xk. And we end up in B, f of x0, f0 of x0, and f of x1, sorry, xk. And the degree is now 1 minus k, or with the yellows, so if we add ones here, then it's just degree 0. Degree 0. So, and then there's again some relations, and now it's as follows. So so we can first do a product in A, and then do something with F, and we take the sum over all possibilities, and this should be the same as the product in, well, now we want to do mu B at the bottom. And then, well, we need to have entries in B, so actually we have to put F's everywhere here. Okay, so it's, so you take all possible things where you have several F's combining things together in B, and then take the product in B. It's the same as first take a product in A, then one F, and like that. And again with the signs. But so just like before, there are no signs if you write it in the tensorial way. So, and of course, if you think about it, if there's no higher F's, then it will be an ordinary functor. Okay? Good. And so now we can, okay. So the F1s actually, the F1s, if you work out this thing with the F1s, so it means actually that F1 commutes with the mu1s, so the F1s are morphisms of complexes. Morphisms of complexes. This is for the mu1s. Okay. So this means that we can say F is a quasi isomorphism, if and only if the F1s are. So we say F is a quasi-isomorphism if the F1s are. Okay. So, and there's then the famous minimal model theorem. Minimal. Well, originally, I think in the settings of algebras, it's due to Kadishvili. And what does it say? Well, for each A infinity category, there is, it can be A, there is an A infinity category infinity category B, and functors A infinity functors. So we got such that mu1b is 0, so this means that this is the meaning of a minimal model, so there's no differential on it, and f and g are quasi-isomorphisms. Okay, and this, and so it means so it means indeed that you can move on this slide. Okay, and there is, so let me note there is an explicit construction of the mu b's using trees. So, but it's, let's say there is it's a too explicit construction to put on the board. So, okay, so but you can really, so if you want to calculate this structure, you can do it. Not that you want it, but you can do it. And so, but it also depends a bit on your choice. So these are not, so you can have different morphisms. So you can have different versions of this category, which are all which are all equivalent. So there's an equivalence. So, but it depends. So which you have depends a bit on your choice. Okay. So, but this is good. How far am I? Okay. Good. So let's do. So let's. I want to use two running examples. Oh, this is very wet. I want to use two running examples to explain some of the rest of this thing. And so let's first start with an ordinary algebra. So one thing you know, so we have so if you have a quiver, so if Q is a quiver, then what can we do? We can make KQ the path category. And so, so it means that the objects are the vertices, and the morphisms are linear combinations, linear combinations of paths. And then the products, well, here we are going to do just an ordinary product. So this is the product. So it's mu1 will be 0, mu3 and higher will also be 0, and mu2 will be concatenation. So that's just turning the path algebra in the ordinary way into a category, concatenation. And yeah, so we put everything in degree 0, all in degree 0. Okay, so that's so there's a so this is yeah, a very well-known category. You can also identify it in a more representation theoretic point of view. So this is also the same as the full subcategory of right CQ modules, right CQ modules containing only the elementary projectives. Okay, the elementary projectives, for each vertex you have a right module V CQ, and yeah, you can check that this is the home space between the projectives. So it's a full subcategory of mod CQ, of the traditional category right mod CQ. Okay, so that's one we're all familiar with. So this has no higher structure, and now I'm going to do one with a higher structure. Okay, so now I take a specific quiver. So I take my vertices like this. So I take a cyclic quiver. Okay, then I have my objects E1, E2, E3 until En. And then I have alpha 1, alpha 2, alpha 3, and so on until alpha n. Okay, and so now we say, so let's call this category, yeah, I'll call it just C. So the objects are again the vertices, C's. Now the home spaces, so C E1 EI plus 1 is just C times alpha I. C E1 is just C E1, and then C E1 EJ is 0, and I is well, when J is not equal to I or I plus 1. So, and what we do, well, mu1 we put 0, mu2, well, well, we use these as identities, so these work as identities, but we could, in principle, we could multiply those two, but we say that their product is 0. So mu I plus 1 should be equal to 0. So you make it as 0 as possible. You don't make it 0 for the identities. So this is as 0 as possible. And then we have mu3 and so on. Well, there's not much we can do. Well, there are no morphisms if you compose more arrows. The only thing you can do is, well, if you go around a full circle, then you can have a product. So you say mu n of alpha. So yeah, now you have to, yeah, I had to put alpha 1 and so to make the composition. So it's alpha I plus 1, and so on until alpha I plus n. So if you do, I plus n minus 1. So if you go the full circle, that's E. So we start with I, so that's EI. Good. So this is a second one, which this is an A-infinity category, and that's also an A-infinity category. And so what I wanted, well, we don't have a bit behind schedule, but what I wanted, what I want to say in a sense is that these two categories as A-infinity categories are derived equivalent for the so C Q of with Q 1, 2, and minus 1. This one is derived equivalent to the other one. Okay.
So don't you need to assume something on the degree of C?
Yes, I forgot. So yeah, very good. So this has degree 1, and this one has degree 0. Thank you very much. So in order to make sense of this, we have to define like what is the derived category of such a thing, and the correct setting is well, we need to, well, here it's quite clear. So how can we make the derived category of such a thing? Well, actually, you start with the projectives, and then you make complexes, and then you take the homotopy category. And now here we also want to do something. We start with this. We want to make complexes, and then take and then yeah, you kind of go to homology. So I'm going to explain what I mean. So in the A-infinity category, there's a notion of a complex which kind of does the same as there, and that's called a twisted complex. Twisted complex. Okay. And so what you do, that takes complex over C. So what you do is, well, these objects, so what you do is you take some kind of formal direct sum of xi and I. So you take a sum of with xi in C. So you take a sum of shifted versions of your objects, and this shifts is to define, well, we will use something like, well, the homs from xi to yj will by definition be like C x y shifted j minus I. Okay, so we kind of assume this, and so it makes sense to extend your category to include all these direct sums, and then so basically you now make a graded module, and then you need a differential. Okay, so we add a differential, so we add a delta, and so delta will be an element in this hom of to itself, and you look at the degree 1. So degree. So you take a degree 1 homomorphism in this, where you interpret well, you bring out the direct sums and you interpret this in that way, then this makes sense. So we take a degree 1 and we say it's tensor nilpotent. Nilpotent. And that means that, well, if you multiply it with itself, but you do not use the mu's, but just tensor products, it will become 0 after a while. Okay, so this is to make sense of things. And then we need this differential. Well, here we have that it's a differential, so d squared is 0, but here we need something similar, so we write mu of delta plus mu of delta comma delta plus mu of delta comma delta comma delta, and so on, should be 0. So instead of just mu squared is 0, here we need all this to be 0, okay? And of course, that's why we need this, otherwise this doesn't make sense. Okay, good. And so there's also this thing, so then we have this TWC, these are the twisted complexes, so these are the objects, and then we have mu's on these twisted complexes. We can also define an A infinity structure, and it's as follows. So the home spaces between two such twisted complexes are just these home spaces where you here have an x and a y, and then you have products, and the products are the higher products if you take something like F0 or F1 until Fk, if you such have products. So what you do is, this is the sum over all these F's together, where you just do deltas in the middle. Okay, so you put some deltas here, some deltas here, and some everywhere in between all the F's you can put some deltas. Okay, and of course these deltas depend on where you start. So this will be deltas in your first object. Then here, after the first F, you will have deltas in your second object, and so on and so forth, and like this. And you take the all possible sums, and again, this is finite because of this condition. Okay, and then you have that TWC is an A infinity category, and and the statement now is that so the theorem that I want to illustrate is that so the derived category dB mod of K, this particular Q, is quasi-equivalent, so there's a quasi-isomorphism, quasi-equivalent, so there's a quasi-isomorphism A infinity functor, equivalent to this TWC. Okay, so this is making sense of the derived equivalence between those two. Okay, so I have 1 minute, or how many minutes do I have? Okay, so I wanted to make this a bit, but I'll continue next lecture with making this a bit more explicit. But what I want to say is actually, so how should you think about this? Well, actually, this category is the category of the projective modules, And now, if you forget about this last one, then then there's this should be thought of as the category of the simple modules of your quiver. But the ordinary homes between simples are very simple. So there's just by Schur's lemma, there's nothing between the homes. But what are these then? But there are extensions between simples, and so these things should be thought of as extensions, and then the mu should these higher mu's tell you how these extensions fit together. So the X algebra of the simples is actually an A infinity algebra, and this is contained in here, and there's one extra vertex to make it more symmetric, and that's the shift of the projective that goes that has dimension vector 1 1 1 1 1 on all the things. So there's this. So if you only look at these is all the simples, and this is like Pn shifted by 1, and that's the endomorphism ring of this whole thing. Sits inside here, and actually the A infinity structure on it kind of is reflected in here. Okay, so this is so normally if you want to find kind of derived equivalences, or Morita equivalences, you need to find projectives and then look at the endomorphism ring, and then you get a Morita equivalence. Here you can work with all kinds of modules, and you look at the X algebra with some higher structure, and this also enables you to recover the whole derived category. So that's kind of the idea. So it's, let's say, so the slogan is it enables us to reconstruct dB mod CQ from the simples. Next algebra of the simples. Okay, good. So next lecture I will come back to this and see how we can interpret this in a geometrical way, and how this gives rise to some intersection theory of curves on a surface. Okay.
Any questions?
So this is the point.
Yeah.
Test. So just to go back to the point on that one, is there something like the X algebra, which has a DG structure, I guess?
Yeah, so the X algebra has an A infinity structure.
Oh, yeah.
So the idea is, so if you got some modules, you take the projective resolutions of these modules, and then you take the endomorphism of this projective resolution, and then it's a DG algebra, and then you take the homology of that, and this is another A infinity. So you actually take the minimal model of that, and that's your A infinity X algebra.
Yep.
And that contains all the information you need to reconstruct the whole category.
Thanks.
Further questions?
Yep.
Thank you. So, is there any fix if you introduce some quadratic relations in your cyclic quiver, and if you possibly have some quadratic relations between two consecutive arrows? Can you modify these expressions?
Yeah. So if you for instance, so what will happen is, so if you start here with some path algebra with relations, then of course you can make the same category. And then if you take the simple representations of the basic simples of that category, then the relations in the algebra will give you a higher x between the simples, and so that's how the X algebra of the simples sees the relations of the algebra which you started with. So
You capture them at level x2.
yeah. So for instance, if you got a relation with a term of a path of length n, then in the X algebra of the simples there will be a mu n, which with the coefficient that captures this, the coefficient of this relation. Yes.
Thank you. But in your example, cyclic quiver does have length 2 relations because mu2 is.
Sorry, I didn't quite catch that.
So just to avoid talking cross purposes. I mean, in your example, the cyclic quiver does have length 2 relations because mu2 is.
Well, this one has length 2 relations. Yes, but then of course you can. So this one has length 2 relations. Okay, so if I then look at this as an algebra, and then look at the simples of that algebra, then actually I get back to there, and then there's so it's some kind of causal duality. Yes. So of course here are relations, there are none, but then the relations over here are encoded in the product structure over there, and vice versa. Yep.
The arrows in degree 1 in that example, not 0.
Yes.
Yes. Yeah, so here are the arrows are here are degree 1 and here they are degree 0. Okay, but then of course you can also shift here the degrees, and then everything will shift, and then look at the Excel. Yeah, so there's different degrees, combinations, but in the case of causal duality, these degrees coincide, and then you can do more. Yep. Okay.
Yeah, I think since the next talk should have started a minute ago, let's maybe stop here and
Yep.